Okay, thanks, Chairman, and distinguished guests. Good afternoon. Today, I'm going to talk about the computational aspects in underground structure. Usually, I'm myself working on civil engineer, usually involved with mutual construction of the foundation or tunnel, something like that. Today, we are going to talk about the 4 parts. One, I will give you an introduction of several cases of large construction happened around China, I think. The second, I will talk about what challenge we'll be facing during the computation for the performance of underground structure. And the third part, where I will focus on some topics, how to solve it. And a short summary will be given to you. And before my talking, I will also introduce my several colleagues of my group. Some of the work are also done by Dr. Yu, Haitao Yu, and also Dr. Xian Liu. And also, we get other colleagues right now, some working in other universities. For the cases of large construction, like we found there are a lot of construction of high-rise building happens, I mean, worldwide, not only in China, also in other countries. This figure showed the high-rise building and construction of the Shanghai Tower. It's just opposite the barn. I'm not working on the up structure, but the basements. Usually, for the high-rise building, the basements will be put and excavated very deep. You will find the person who working on the to prepare the reinforcements looks very tiny to compare with the huge foundation. The depth of this excavation bits is around 36 meters. For sustain the high-rise building more than a million tons, the huge flats of the mass concrete should be casting. So the same stress during the hydration heat would be a major concern of this. And also, another urban underground involved with the metro lines, also the substation for electric power, and also some cultural architecture for musician or something like that would be involved largely compared with the construction before. An example of this is the metro line in Shanghai is more than, right now run is more than 400 kilometers. And for the urban construction, this slide shows the water supply project happening in Shanghai. It's the mouth of Yangtze River. To supply the clear water for the people living there, it's more than 25 million. So a huge reservoir should be constructed here. And also the pipeline should cross the Yangtze River and also transported to the whole city. So the total length of the tunnel or pipeline is more than 230 kilometers. And another extreme engineering for the transportation, like the linkage between Hong Kong and Zhuhai and Macau. This project is about 35 kilometers in length. It's composed with bridge and also tunnel to cross the two artificial islands to form the whole project. To construction those kind of the linkage, we should build the bridge, the foundation, the pier for the foundation, and also the artificial island to be built to connecting bridge and tunnel. But for the tunnel, we should prefecture the segments and shift it to the construction side and the sinkings and to form the whole lines. So for the process of another way of construction tunnel, the another type of the tunneling method, the shared tunnel or TBM tunnel, the segment will be assembled segment by segment to form a huge tunnel. This also should be taken into account for the typical challenge. For the challenge, we should face like this, because the infrastructure will take a huge sum of money. So its serviceability during its running, its operation is very important, because underground structure usually working in not such a good condition. So the leakage of the water into the tunnel or corrosion, even in some cases, the pier, the foundation will be also suffered from the durability problem. Another problem is the huge, massive concreting, because the hydration head is very huge during the process, the concreting process. So you will find that the little cracking on the surface of the concrete wall. This is another issue about the safety. Usually, underground compared with the upward structure, it's difficult to put out the fire if there are some accidents to fire. So that would be influence the safety and the durability and also the suitability of the underground. Another safety issue is about the earthquake. You know, with the dimension growth, the earthquake might have some unwilling effect on this. Unfortunately, we are inhabited in a world with full of the earthquake. This slide shows there are two regions of earthquake. One is around the Pacific Ocean, and another one is just between the European continent and the Asia continent. We had also some cases of the damage induced by strong earthquake. Unfortunately, there are so many earthquakes. This is only recorded for just several hours. So if you visit the website of Nice, you will find that there are a lot of earthquakes happened frequently, time by time. To account for the earthquake, usually the engineer had some simplified model. It would be account the deformation longitudinal or the creep during the earthquake, and also the snag moving of the tunnel, or even in some cases the cross-section overlaying or racking. That is the understanding of from the engineer, from the practical side. And also we could use simplified beam model to model the seismic behavior. We could also model partially the soil, and also we can also model partially of the joints. But it's also in a global behavior, not specific to typical points. Even though this simplified model could give the internal forces in the tunnel, and also the maximum bending moments of the joints, but it's difficult to give details of the mechanical behavior. So some research had also developed a typical method to simulation the joints between the segments. It developed a 19/8 node frame to simulation this behavior. But in some cases, the engineer not only wants to have the global behavior, he also wanted to know details of the local failure of the structure or tunnel under the seismic loading. To account for those kind of projects, if the pipeline crosses the river, damaged during earthquake, that would be tragedy to the people. 25 million people with no clear water, so that would be a tragedy. So the consulting company wants to know what would happen to the huge project if during the strong earthquake. But the difficulty for us to compute such a huge size will need more resources and computer. One, you will find that the length for the motor is about 12 kilometers, and the width of the motor would be 2,500 meters. And for the soil in Shanghai at the mouth of the Yangtze River, to get to the input from the bedrock is about 300 meters in depth. If we want to get detail of this solution, that would be needs to take huge facility for computing of this and huge time to constitute the model. What should we do? I will not talk all of the challenges we face. We just focus on these two. One is seismic performance of the tunnel, especially land tunnel. Another one focus on the multi-failed process. For the scale I had mentioned before, from the sides to the details of the sealant, this figure shows the hillsides. This figure shows the partial of the tunnel is of this scale, and this figure shows the assemblage ring of the tunnel. It's also consists of the bolts and also sealants. So the scale will be wider. If you want to know details behavior of the sealant, and in the huge size is what we should to constitute a method to solve. Usually, that problem could be expressed in this kind of state of equation of the system. This part is the kinetic energy, and this one is potential energy. Usually, we account of the straits of strain. We just focus on the potential energy. It's decomposed as the external force, internal force, and also the damping force. We could compute it with a widely closed mesh. That would be not what we want to get, especially for the bolts, the force in bolts, and also the straits in sealant. If we mesh, make the fine mesh at the sealant scale, millimeter scale, that would be huge number of the elements and the knots. So the difficult. Initiates we had also retrieved back the method developed by Professor Lackner and Professor Mang about the adaptive mesh method. We think that it's workable. If we use that kind of method and we just to consider the close mesh and also the fine mesh, we don't need to update the mesh. That will be introduce interface, the overlapped area. If we can develop or deduce some formula for this area, so we can solve this problem. This is just as Shaw had developed this so-called bridge doming method. So we use this idea and developed the ruler for the interface to consider the energy of Hamilton and introduce the Lagrange multiplier for to account for the difference between the close mesh and the fine mesh. If the constraints could be minimized, we can constitute the updated the Hamilton. In that case, we should modify to introduce this force of Lagrange for the refined domain and also for the fine domain. So, if with this method, we can use the traditional finite element model to simulation the close behavior and go to the multi-scale fundament to the habit model and get the final results. There another problem about the dynamic response during dynamic input, because if the whole computation will depend on the fine mesh, that would be time consuming. So we start only from the close mesh and will be stopped in between the fine mesh. That was called the habit time step for this. This figure gives a validation of this method. This is a cantilever beam. It's of the span around 3 meters and the cross-section like this. The mesh scale is the cos over fine is about 5. So this figure gives out the analytic solution and also the mass scale solution and full refined solution. You can find that it's quite close. Not the same, but quite close. With this method, we applied to typical pushing of the antenna, and for the specific pushing, we use the refined mesh, and for the other part, we just use a fine mesh. So we can also introduce the traditional soil structure between the use the penetration method. It's no news for this part. In these cases, we can do this heavier calculation of the huge sites. And during the huge sites, we can also get the details of the solution at the what we concerned about. So it's workable for this large-scale seismic response simulation. But during the simulation, we found that there are several parts, maybe of significance during the seismic process. But use the traditional method, continuous mechanics method, it's difficult to get the failure process. So we try to use the same method to develop a discrete and continuum coupling between this. This just shows the example of a beam. The same formula had developed like this one. And also the Hamiltonian is also the same. We can start the continuum calculation use the commercial software, and also use the particle flow component for the discrete pushing. This slide shows the interaction between the particle and also the continuum. You will find out that it's really can simulation the cracking process. This one just shows the particle, but next figure we get the this pushing use the cross mesh, the traditional continuum. This pushing use the discrete simulation with the PFC. You will find that the cracking time is the same, and also the difference of the maximum force is only less than 1%. I will go to the next pushing about the mud-field process. For the challenge of early edge cracking, it's usually would be dangerous for the project, for the structure, especially under the water. During the prefecture of the segment, to avoid the cracking at the early edge, the whole process composed of this pushing, like the preparation of the material, the aggregates, cements, and sand, and also water. And the second is to cast in the segments and curing with formwork, and move formwork and curing inside, and put it outside and curing outdoor. To account how the process, what will happen during this process. So traditionally, we know that the elastic model and strength will evaluate with the hydration process. And we also know that there are some drying shrinkage will happen during the cooling process. But that would be needs many tests to find out this relationship. Previously, we had also used the so-called the coupling of the weak coupling of the fields, the temperature, the moisture, and the stresses, to account of the heavier total strain would be happened during this process, and found out that we can assume that the same stresses can be calculated in this one. So we need to know the temperature variation during the hydration process, or even under the radiation of the sun. And we can get the hydration heads process, but the distribution of the temperature should be similar to use the finite element or differential element if we give the boundary condition. And for the strain from drying shrinkage, we can also use the process suggested by Professor Bazan. And if we get the relative humidity in the whole member, we can develop some formula to calculate the drying shrinkage. And for the creep, it's easy to use the traditional formula. If we put all this together, we can calculate the stresses and the strain during the hydration. This one shows the validation through a simplified experiment. We measure the temperature and also this strain with tips. This one is calibration with the measured one and also the computed one. This method also applied to practical work, but that could only consider the pushing of the cooling outside, because the drying shrinkage may be of significance. To simulation the whole process, we had found that at an early age, especially 3 days or 1 day, it's changed more quickly than the cooling outside. So the problem is should find out which parts would influence the manufacturing quality control. So the full coupling method was developed based on the formula developed by Gavin and Professor Schriffler for the whole process. This different color account for different pushing, the mass balance of the water and also the entropy in different processes. But for the mechanical property, we can use the large-scale method developed by the macro-mechanical, like H by inclusion. If the mechanical parameter can be estimated use the previous method, like this one, if we had the pushing or component of CSH or the C3S, or even the aggregate, we can estimate the final parameter. With that parameter, we can input to simulation the process of the hydration. We can also compare with the full coupling model with the previously weak coupling model. We will find that there are some difference. The red line is a full coupling for the temperature differentiation, and the purple line is for the weak coupling. We will find that the thermal shock and also the stress shock would happen during the demodeling or remove the formwork. But for the weak coupling, we are underestimate the effect of the semi-shock. For the modern concretes, they had another effect, especially during the early age, where they, like 1 day or 3 days. So even it had the formwork, it's also difficult to know that if something happened from the chemical reaction, we call that autogenous shrinkage. It's different from the drying shrinkage. So what could we do for this? We can also think of that the total strain can be measured. If we can, in the previous we also measure the elastic parameter for the many tests, we can find that. And for the semi-strains, we can also measure temperature, but we can't assure that the expansion coefficient of summer would be constant, especially during the early age. It will be changed with the hydration process. And if we can also estimate the autogenous shrinkage, that would be also good for prediction the total stress increments. We also noticed that the another way to do the multi-scale analysis applied to chunk and to ceramics and also to rock mechanics. If we introduced the local coordinates to represent the inclusion in a fine part, that given an equation would give like this one, and if we get the boundary condition and also introduce the differential formula, we can get the stiffness of the homogenized matrix. That's what we expected to get the the mechanical parameter. Based on that method, we also developed the so-called the multi-scale simulation of the process with the mortar scale. If we assume the past scale is homogeneous, and we can get the mortar scale and the concrete scale, and finally we can also get the member scale. In this case, we assumed that double scale can be assumed. One is with the macro scale, and another one is meso scale. Finally, we want to get the macro scale with the same formula, and the difference is the differential formula we should do expanded to 2 coordinates. In these cases, we can get the given equation for elastic modular, like this one. If we get the boundary condition for displacement and for the force, we can get the stiffness from the matrix function of the macro scale to get meso scale, and finally get the macro scale. This figure shows the calibration between the predicted one and the practically measured one. That could be workable, I think. And also, we could apply the same method to predict the coefficient of semi-expansion, like the similar formula. This gives validation of the expansion, the coefficient of semi-expansion. We have found that at the early age, it's changed rapidly. This also compared with the experiment measured one and also the predicted one. And for the autogeneous shrinkage, we can get the motor scale and also concrete scale. We can also compare with the experiment one in motor scale and also the one in the concrete scale. So it's kept quite good, I think. With those parameters, we can start the simulation of the whole process with the traditional finite elements. This one shows the scale, the tests of the full scale tests of a specimen is of the 853 cubic meter for the whole segments. This figure shows the measurement of the whole process. And with this simulation, we can find that the temperature is very close to what we have measured. And also the straits is quite similar, but the strain is quite fit, yeah. But for the concrete, it's very brittle, especially at the early age. So it's around the 70 micro strain. It would be cracking. So to improve this, we should start from the preparation of the material. So the so-called high-strength fiber was introduced, and the similar process had also applied to the simulation of the material, and the nano attention method had been used to calibration the strains. Right now, we just can estimate the linearity and also the elastic limits. But to experiment, and the engineer wants to know the whole process, so we still need something to do. So finally, I will give a short summary for what I talk about. The first is to balance the computer resource and the requirements. The so-called large-scale mesh method I have developed for the seismic analysis. Based on the same method, FDM and DEM is also developed. And a habit time step is also adapted to get the reasonable accuracy during the large-scale computation. And with the concept of mass scale, we also want to develop a multi-Shanghai type of tests for the tunnel. Yeah, if you do the whole test, it would be cost greatly. And for the modified of the early age concrete, although the weak coupling method adopted widely in practical, but the full coupling indicates that they are also significant. And for the time-dependent behavior of the modified of concrete can be modeled through the stochastic mass-scale model, just like presented before. But we still found that for the components and models of elasticity we can get, but for the elastic limits and other parameters, maybe we need more work to develop this method. And I would also appreciate my sincere thanks for Professor Mang and Professor Cui, and also Professor Lactau from Ghent University and Professor Bobet for all they have contributed to the work of my just presented. Thank you for your.